In this video, we worked through the derivation of the quotient rule algebraically. Last time we stated the quotient rule without proof. This time we want to prove it. I actually haven't ever done this derivation before, to be honest. So I'll be doing this for the first time with you. We'll see how it goes. So here we've got the derivative with respect to x of f of x over g of x. If I call the top function the high function and the bottom function the low function, we use this mnemonic to state this rule. The derivative of high over low is low d high minus high d low over low low. And the d is an operator. It applies to the function in front of it. So it's low, that's the bottom function, times the derivative of the high function, minus the high function times the derivative of the low function over the low function squared. So when I'm writing this rule, I say to myself, okay, low d high. So it's the bottom function g of x times the derivative of the top function, that's f prime, minus high, that's the top function, f of x, times d low, the bottom function, you take its derivative, over low low, that's g of x quantity squared. And we know that the limit definition of the derivative of a function is given by this expression. We just want to show that the limit definition of the derivative of this actually equals this. So we're going to just write down that limit definition for that particular quotient and then try to algebraically rearrange things so that it looks like this, keeping in mind that f prime and g prime are represented by limits similar to this one. So we've got the derivative of f of x over g of x is equal to the limit as delta x approaches 0 of this function evaluated at x plus delta x. So we're going to have f of x plus delta x divided by g of x plus delta x minus the original function. So that's f of x divided by g of x. And we're dividing by delta x. Well, the first thing I notice is that I've got fractions within fractions. So one of the first things that I'll do to get rid of that sort of problem is multiply by the least common denominator. And the least common denominator in this case of the fractions within the larger fraction is g of x times the g times, or g of x times g evaluated at x plus delta x. So I multiply by g of x times g of x plus delta x. That's fine, that's legal as long as I do the same thing in the denominator. And you can kind of see that we're going to have a g of x times g of x, that g of x squared down here when delta x goes to 0. As long as we can get rid of this delta x, it's going to 0. So this has two terms. We're going to distribute. And when we distribute, that's going to clear the fractions in the numerator. All right. So I've got this right here. This equals the limit as delta x approaches 0 of this times this. Now the g of x plus delta x is going to reduce. So we're just going to end up with f of x plus delta x times g of x. And we subtract this fraction times this. Here the g's are going to reduce and you just end up with f of x times g of x plus delta x. Now this looks very familiar. It looks very similar to what we got using the product rule. So I have this expression and I want it to look like this. So the expression for f prime has an f of x plus delta x divided by delta x as one of its terms and a minus f of x divided by delta x. Because we know that a plus b divided by c is a over c plus b over c. So I'm just using that rule in reverse. If I have two fractions with the same denominator, I just add the numerators to get the sum. The same is true here. If I've got multiple terms in the numerator, I can separate those into separate fractions. So I'm looking at this f of x plus delta x divided by delta x, and I'm trying to make that that expression that I have here, this f of x plus delta x divided by delta x, match this one right here. But the problem is that it's multiplied by a g of x. Now we've handled something like this before when we added and subtracted just the right thing to get rid of that in the derivation for the product rule. So This is a very, very similar technique. I've got f of x plus delta x times g of x. And I want to subtract f of x from this. I can do that as long as I also add it. Sometimes it's called adding a well-chosen zero. So I've got, I need an f of x times g of x here. And that's all divided by delta x times g of x times g of x plus delta x. And we're subtracting that there, so we need to add it to compensate. That way we don't change the numerator at all. It's just the exact same thing. And then we regroup. We're going to group these two together and factor out that common factor of g of x. And group these two together and factor out that common factor of f of x. So I have a g of x here. And then I've got f of x plus delta x minus f of x there. And I want that all to be divided by delta x times g of x times g of x plus delta x. Now I know we could reduce the g of x's, but we don't want to do that because notice in our quotient rule, we've got that g squared in the denominator, and I have a g here. Like you could have simplified that. You could have taken this and divided by the g squared and simplified, but we never do that. We always write that quotient rule as an actual quotient at the end. So I'm going to keep this g of x times g of x plus delta x in the denominator. Then I'm just going to write it as a separate factor. So that this times this times this equals this expression. Because if I distribute that g to this, I get this. And then there's an implied one there. If I multiply this by this by this, I get that denominator. So this is all of this piece. And then we're going to add this expression divided by that. I notice that they have an f of x in common, so I'll factor that out. And then I've got a g of x minus g of x plus delta x. And I want to divide that by delta x. And then I'll multiply by 1 divided by g of x times the quantity, or times g of x plus delta x. All right, so it's starting to look like our quotient rule already. This, if I take the limit of this expression as delta x goes to 0, I know that that's f prime by definition. And if I take the limit of this expression as delta x goes to 0, gosh, it looks a lot like g prime, but the order is wrong. I've got g minus, or g of x times, or minus g of x plus delta x. And I really want it to be the other way around. Well, that's easy enough to fix. If I factor out a -1, I'll put a negative there and make this positive and that negative. -1 times that g would give me the original negative g, and then negative times negative 1 times negative g of x gives me positive g of x. So if I distribute the negative here, I actually get this. And now the limit of this as delta x goes to 0 is g prime, and I have a minus there. And then I've got 1 divided by that expression there. The multiplying by 1 over something is the same as dividing by it. So we can write this as g of x times f of x plus delta x minus f of x divided by delta x minus f of x times g of x plus delta x minus g of x divided by delta x. And we're taking all of that and dividing by g of x times g of x plus delta x. And I think we're almost there. If we take the limit of this, the limit of g of x is just g of x. And then we have the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. And then we're subtracting f of x times the limit as delta x approaches 0 of g of x plus delta x minus g of x divided by delta x. And again, the limit of this expression and this expression is just the original expression because these are constant with respect to delta x. We're thinking of x as fixed at the moment. So the limit of a constant is that constant. So that's constant, we just bring those down. And then as delta x goes to 0 in the denominator, the g of x is treated as a constant, but this is going to approach g of x plus 0, which is just another g of x. G of x times g of x is, of course, g of x squared. So I've got g of x here, and this is the definition of the derivative of f. That's f prime of x. And then we subtract f of x times this expression, which is the definition of g prime. And then we're dividing by g of x times g of x, which is g of x quantity squared. So that is the derivative with respect to x of f divided by g. And let's check with our mnemonic if this is the high function and this is the low function. Do we get low d high, bottom function times the derivative of the top function? Yes. Minus high d low over low low. So yes, it checks out, and that turns out to be our derivative. All right, so now we've proved it. This is how you compute the derivative. Most of the time, we're not going to use this limit definition of the derivative. We're just going to use this quotient rule instead whenever we've got a derivative of a quotient.